Hello, statistics class. So you should be watching this video once you've finished your reading guide and you're right near the end. So we're going to look at our first example of a hypothesis test for means where we aren't sure about the population mean and hence have to use t-procedures. So let's have a look at this one. So go ahead and get reading here. It says we've got a professor at a large university. They believe students are taking an average of 15 credit hours per term. And so this professor takes a random sample of 24 students, and the class has 250 students. This is the total number of students in the population of interest. And this is the result of that sample. So this must be like credit hours, right? So this is, let me get a thinner pencil. This is going to be credit hours. Taken by those students. Okay, so the question is, does this sample indicate that students are taking more credit hours than the professor believes? So let's start out by thinking about what our population of interest is. Same procedure we've gone through the whole time. So our population of interest is, I think, students, but not just students. We've got to specify where. This is students at this, we don't know which one, but it's this university, so we shouldn't extend our results, I'm already thinking about that, past this university. Our variable of interest is, of course, credit hours. We've already got that up there, so I'm just going to say CR. Let's see, should we just go to our hypotheses? I think so. So our hypotheses. So H sub O, remember we should only ever have parameters in our hypotheses. So H sub O is going to be mu, the true mean number of credit hours that are being taken. So we'll assume that the professor is right. In other words, nothing unusual is true. So we'll assume 15 credit hours. And are we interested in more, less, or different? Does this sample indicate that students are taking more? It says right here. So I'm going to say my alternative is mu is greater than 15 credit hours. Okay, so what do we think about for our assumptions? And what do we know, by the way? I guess I should write that down. What do we know? We'll go to our assumptions in a second. So I think we need to go to our calculator in a second to come up with what we know. We need to figure out what our sample average is. So we are going to need x bar. We're going to need the sample standard deviation. And I think we already know n is 24 students. We're going to have to use our calculator to get those, or else we'd have to do a lot of math by hand. So we'll get those in just a moment. I think we should just go ahead and address our assumptions while we're here, though. So let me get a text box. So let's type out our assumptions. So random. Remember, we definitely, for means, have a looser criteria for randomization. So this person says they took a random sample. So a random... This was stated to be a random sample. Remember, it's okay to be a random if you think that the representation out of the population of interest is essentially random. That's okay, especially for means. You have a little bit looser criteria here, like I said. 10% doesn't matter as much for means, but we still want to check it if possible, just to make sure we're not sampling too much. 10%, let's see, so since we have 250, which is more, which 250, which is, since, let's say it like this, since 24, 240, since, let's say it like this, since there are more than 240 students at our university, I'm going to say at this university, we've got 250, so 250, in fact, we are good here. And the last thing, we don't have NP and Q because we're not doing proportions. The most important thing you've got to check for this is the central limit theorem assumption, which we're going to call the nearly normal assumption. So we need to know if this data is nearly normal, and to do that we need to check a histogram. So I think we've gone past the point where we can get away without using our calculator. So let's bring up our calculator here. I'm going to shrink it down just a bit so it fits in our window. Okay, so the first thing we want to do is enter our data. So you want to put your data in your list. I already entered all 24 students' numbers of credit hours in my list, so you can see that down here. Let's just double check that it indeed is in there. So if we go stat, edit, we could go ahead and look all the way down to this list. I think you can go all the way to the top and get it to go down that way. Yep. All 24 numbers of credit hours are there. So I'm going to go back out to my home screen and compute by going stat, calculate. So I'll go over and get one variable statistics on list 1 and calculate that. Okay, so it looks like we have on average in this sample 16.6 credit hours, and we're going to use S sub x because remember this sigma sub x thing is always fake, kind of. We're not going to get into that now. So our sample standard deviation is 2.223 and x bar is 16.625. Before we go out and write those down, well, you know what? Let's just go out and write those down. 16.625 and 2.223. So those are things that we know. 16.625 and 2.223. Okay, so for our nearly normal assumption, we need to check the histogram. So let's go and look at the histogram of these. We've already got them in. I'm going to go to second y equals, make sure that my histogram is on. Looks like it is. Okay, I'm good to go there. So I'm going to go graph. Didn't show up. Oh, I got a zoom 9 for zoom statistic. And there's my first histogram look. So does it look like it's nearly normal? Well, it's symmetric. It looks like mainly multimodal. We could, of course, mess with the bin size. So let's go to our window and change the bin size just a bit. Let's make the bins a little smaller and see if it changes what this looks like. Makes it look really skewed or something like that. We have a pretty big sample size, so it shouldn't worry. As long as it's roughly symmetric, we should be good to go. Let's look at that. Yeah, that definitely looks roughly symmetric. So what you want to do on the AP exam is take this guy and sketch it, just a rough sketch, kind of say what the bin size is at least. So I'd want to say my bin size was 1. So I'd sketch that right here. I guess we could get a screenshot and try to put it in there. Let's try to do that. So I'll go and see if I can grab a screenshot right here. And I'll slide that into place if it lets me. Oh, it doesn't look like it wants to let me. Nope, but anyway, that's how you would do it. So you take that and put it right here. So we'll just, and then you want to describe it in words. You can't just draw it down, you got to describe it. So we're going to say since our histogram is roughly unimodal and symmetric, the central limit theorem applies and our sampling distribution will be nearly normal. So really key language there, so definitely practice it as you're starting out especially. Very key on that one. So we've got all that done. I think it's time to go ahead and actually create our test statistic and see what happens. So instead of saying Z, we're now using T procedures. This is a single mean T procedure. So we're going to get a T going on here. So we're going to say T equals. And how do we do this? I think we do it the same way before. We go statistic minus parameter all over our standard deviation. So that's going to be our statistic is x bar. So we're going to go x bar minus our parameter. Well, we wanted to compare it to 15. And our standard deviation is now going to be our sample standard deviation over the square root of n. Square root of n. So let's go put that into our calculator and see what we get. So I'm going to go out to my home screen. Go, what was it? I guess we could go and drop this down a little bit. There we go. 16.625 minus 15. Take that and divide it by, go and say, put it up here and say divided by, what is it? get some parentheses going. 2.223 divided by the square root. I need to go hit the square root button of 24. Okay, so there is our t statistic. So let's go and write that down. So our t statistic here, what was it again? I missed it, dang it. 3.58. So we're going to say this is 3.58. So is that a really unusual t statistic? Well, it depends on which family, on which curve we are in the family. So this is t what? So our t depends on our degrees of freedom, which is n minus 1. So t sub 23 degrees of freedom, I should have put that up here. As soon as I determined this was a t statistic, is it n minus 1 is the curve, the specific t model I'm on. So t for 23 degrees of freedom turned out to be 3.58. What does that mean in terms of a p-value? Let's go and see if we can figure this out the best way we can. So our p-value here, I think I need to say my p-value is between two things. So my p-value is going to be between two things because the t distribution isn't exactly as nice in terms of giving you an exact answer unless you use your calculator. So we're just going to get a p-value between two things, and that should be good enough to make a conclusion. So I'm going to say my p-value is less than one thing, greater than another thing. Let's scroll down and look at the t table. So remember, we got 23 degrees of freedom and 3.58. So you can see on your t table, works very much like a z table, except it's only got one row for each family in the curve. So 23 degrees of freedom is right here. Now we want to be looking for the closest number to, what was it, 3.58? So 3.58, I still haven't found it yet. Looks like it's further this way, right? 3.58. So what's that going to be? It's going to be over here. So I think that's going to be between these two numbers. So what are those two numbers? Well, if you look up at the top, those tell you about the p-value. So the p-value here must be between 0.0005 and 0.001. So let's go and write that down. And we'll know. So which thing was bigger? I think it's going to be less than 0.001 because that's bigger, but more than 0.0005. So that means that basically our p-value is really small. So what do we conclude? Now let's write out our conclusion and get a nice text box going for that. So what is our conclusion? I'm going to say since my p-value is very small, I reject H sub O. There is strong evidence to conclude this university's students are taking more than 15 credit hours. Move that up a little bit to make it nicer. Move it down a little bit. So there you go. Same kind of conclusion that we've done before. Nothing about that changed. The only thing is you have to do a p-value between two things. If you want the exact p-value, you can actually get that from your calculator. The AP exam accepts either one of these. It's very important you know how to do both. On tests, I'll be asking you to do both. Let me show you how to put this in our calculator since we've already got our calculator with all the data in it. So let's look where we're going to go to calculate the exact p-value on our calculator. I think you want to go to Stat, and this is the first time we've looked at this tests menu. So we're doing a one sample z or t-test, so I think that's option number 2, a t-test. So if you go there, you have the option of either directly looking at your data or entering the statistics manually. So I think we have the data already stored in our calculator. You can see it's down here in our list right now. So that's the first thing. This mu sub O is just like what I talked about today for the first time in class, which was it's the hypothesized value of the null hypothesis. So the professor originally assumed that the students were taking 15 credit hours here. This is an easy thing to skip, So be careful not to skip this option. It's so easy to skip. You need to tell it where your actual data is so it can pull it, so it can get this data number. Frequency you leave alone, and then you tell it what was your hypothesis. Was it 2 tails? Was it below, or was it above? I think ours was above. So then I'm just going to go down and tell it to calculate. And it should calculate everything we need. So it says T, our T statistic, is 3.58. It says the p-value is this. You can see it's in scientific notation. You can see this is the stuff that it pulled it from. So that's consistent with what we had, right? 3.58. There you go. 3.58 is the p-value consistent with what we had. Well, let's look at it. It says 7.90 e to the negative fourth. Remember, what's that really mean? That really means that the p-value is 0.000790. If you think about that, I think that number is indeed right in here. So that's the p-value. So there's the way you can run a test on your calculator. You can actually use that on the proportion test that we saw before. So sometimes I'll let you use the calculator to run a test just to save time, and sometimes we'll do it by hand. We just need to make sure that we're comfortable with both ways. So to finish up this example and finish for this weekend's reading guide, I think let's look at a 95% confidence interval. Since we've decided that there's a difference, that it's more than 15, how much more than 15 is it? Let's do a confidence interval. We won't go through our assumptions and all that again. Let's just do the interval itself. So what is the confidence interval? The confidence interval is, of course, going to be the statistic, which is x bar now. Maybe I'll write this one out. I think you've seen this formula before, though. It's x bar plus or minus. Instead of z star, it's going to be t star. And how many degrees of freedom? With 23 degrees of freedom for us. You could put degrees of freedom here if you want to be general. And then that's going to be multiplied by the standard deviation of x bar, or of x, doesn't really matter, divided by the square root of n. So for us, that's going to be 16.625 plus or minus t star for us for sub 23. Oh, well, what confidence interval do we want to do? It says do it 95%. So we're going to have to go back and look that up. So let's go down here, look in our t table. We're in the 23rd row is what's from degrees of freedom still. And you can go down here and look up your 95%. So we need to go 95% up to here, and this guy right here is t star. You'll notice, just like it said in the reading guide, this infinity column is of course now called infinity. You should understand why. These are the z star values, because if you take the limit as t star approaches infinity, for the degrees of freedom approaching infinity, I should say, you get z. And in fact, that's the answer to one of the questions. If you're not a calculus student and needed the answer to that question, that was one of the answers to the questions in the reading guide, is the limit as degrees of freedom approach infinity of t star equals z star. You could even just put t and z in here. The t distribution, as you take the degrees of freedom to infinity, becomes the z distribution. So that's why we got z star values from this table a while back. So t star sub 23, I've already forgotten what it was. Let's go back down before I put the wrong number in. It's 2.069. Okay, so we're going to have 2.069 times the standard deviation, which was what? 2.223 divided by the square root of 24. And what's that going to be? We'll go and pop it in our calculator real quick. Let's clear this out and say, what was it? 16.225 minus 2.069. And then we've got different alpha y equals here just to make it nice. Uh-oh. No, I didn't want to do that. Oh man. 16.625 minus 2.069 and the times 2.223 divided by the square root. And I have a cat. Square root of 24. I think that looks good with order of operations. There's that one, and then I'm going to hit second entry. Just scroll backwards and say plus. I can tell my guy's a little bit slow. So there are our two confidence interval edges. So we're going to say 15.69 and 17.56. 15.69 and 17.56. Let's interpret it. So we are, since we did a 95% interval with 23 degrees of freedom, we're 95% confident. You can read my handwriting. Confident that the true mean number of credit hours taken by students like these. I could, of course, go back and reference that these are from a specific university, but this is the safest way to do it, so you don't have to think about your population of interest a lot. That's why I've been mentioning that all year. By students like these is between, I have to learn how to do cursive again, 15.69 and 17.56 credits. And there you go. So there's our first T procedure example. And really, you should be ready to start the first homework now. So if you have extra time this weekend, I'd encourage you to do that. The numbers are posted on Moodle. That'll be due on Tuesday. Otherwise, I will see you on Monday, and have a great weekend.